Hello. This talk is called Fine-Grained Role-Based Access Control for Linux using OPA and Active Directory. Before we start, I'd like to extend a huge thank you to Sam and all the other DevSecCon organizers for giving us the opportunity to share our story with you all. Let's get started with introductions. I'm Daniel Popescu. I've been at Yelp for 5.5 years, and I'm the group tech lead for the security organization. In my spare time, I enjoy yoga, flow arts, and solving IAM policy puzzles.
Hello, I'm Charlie Chetin, and I've been at Yelp for almost 2 years. And I've been an infrastructure security engineer, and recently I became a tech lead in the identity and access management team at Yelp. I do enjoy some quality beach time and long drives without planning.
Now we work at Yelp. And if you're not familiar with Yelp, it's a company that connects people with great local businesses. As of the end of 2020, Yelpers have contributed 224 million reviews on our platform. There are approximately 31 million unique devices that access Yelp every month on average. And approximately 500,000 business locations spend money on Yelp ads every month on average to promote their businesses. As you can imagine, it takes a lot of infrastructure under the hood to support an application with that type of scale. Today, we have more than 900 geographically distributed software engineers who design, build, test, and maintain the code infrastructure that powers our product. And there are upwards of 5,000 Linux servers to support these development, testing, production, and various other types of environments. At Yelp, we've always used Puppet code for configuration management of these hosts in our infrastructure. Historically, the Puppet code not only managed configuration, such as which software gets installed, what services are running, and stuff like that, but it was also used as the primary means of defining access control mechanisms for these Linux servers. Believe it or not, the user management component of our Puppet infrastructure was introduced over 7 years ago. Wow, that's a really long time ago. I think the design and implementation decisions probably made a lot of sense at the time, but over time, as the code base, server count, engineering count, and the company grew, we found ourselves dealing with a lot of shortcomings that frankly we felt had to be addressed. So let's talk about the problems. In the original authorization infrastructure, we basically had 3 main categories of users: engineers, ops deputies, and admins. Engineers had SSH to many hosts. Ops deputies had SSH and sudo access to most hosts. And admins were given SSH and sudo on every single host across the environment. The idea was to have 1 to 2 deputies on each team that were capable of doing ops type things for their team members, such as restarting services, deleting files, and other types of maintenance tasks. Over time, we got in a situation where more than 25% of the users had one of these 2 heightened sets of privileges. And the Puppet code was implemented in a way that any ops deputy or admin could easily promote another user to themselves become an ops deputy or admin via a simple YAML change in the Puppet repository. This was super convenient. The Puppet infrastructure also provided a mechanism to add additional categories of user, but it required making code changes. And the code base was quite complex, full of traps, and people often misunderstood how things actually worked. This could lead to frustration for those engineers who understandably don't really want to debug Puppet code to figure out why they don't have access to the servers they need access to. And really they just want to get the access so that they can perform their immediate duties. As a result, what often happened is that the path of least resistance takes precedence, which leads to infamous access requests like this one, in which a user needed to perform a simple debugging task on a single host class that their team is responsible for. And they requested admin permissions for this. And it was approved by their management chain. And as a result, they were granted sudo across thousands of different hosts, including potentially mission critical ones with sensitive data that they didn't have any business need to access. I think this specific access request was the straw that broke the camel's back which ultimately led us to prioritizing the project that we're going to explain to you to improve this system. There were more issues on the operational side. Permission changes took a long time to fully propagate to all hosts, more than 2 hours in some cases. And every time we ran Puppet on a host, the user management component was responsible for more than 30% of the runtime. Due to code complexities, it was difficult to understand the full scope of impact of a permission change, or even know if they would work correctly. And if someone had an access issue, it was really difficult for us to grok why they could or could not access a host. Basically, all we had was SSHD logs with public key accepted or public key denied, and it wasn't very clear why that would have happened. So now that you understand some of the pain points in the original system, I'll hand it over to Charlie to give an overview and a deep dive on the new authorization architecture that we built.
Thank you, Daniel, for the great introduction. And now I'm going to take over this control of the screen. Let's see if I can do this. Yeah. So as Daniel mentioned earlier, this is how the overall architecture looked like. It was all authorization files were managed by a single place called Puppet, and it was monolith heavy and error prone. And even sometimes the broken Puppet runs were preventing to make authorization decisions. So once we know the shortcomings of our system, the natural question was, what is the design goals of the new architecture is going to be? So the simple answer to this question was that we want a system that we can ensure the principle of least privilege in our Linux infrastructure. And we want to be able to do that for a long time in a dynamic and a growing environment. So in this context, if we break down our design goals into actionable items, we wanted to implement a scalable, reliable, and a long-term authorization infrastructure. We wanted to remove all authorization and user management from Puppet. And we wanted to control and audit authorization changes, as well as we wanted to ensure fast policy changes, but that wasn't enough. Of course, when we are ensuring the fast policy changes, we wanted to be able to test those changes to not to disturb thousands of Linux infrastructure. So with these guidelines, we were able to come up with this. So this is the new architecture that we created individual components for enforcing authorization. These individual components collaborate together in order for users to be authorized in each client host. In this way, we totally decoupled our authorization architecture from Puppet, and we put all these things into the individual components. So I'm going to go over each of these components one by one and describe how do they collaborate together. But before that, I would like to show another image that describes the overall architecture of the system to understand what kind of technologies that we use in the background. So this is overall of the system that if I explain from bottom up, basically, we use an access-restricted Git repository to store authorization policies and group definitions. And we use Active Directory to store group memberships. And we put all this information to an S3 bucket and send it to the client hosts. In each client host, we run Open Policy Agent, or OPA, to enforce the authorization decisions. OPA is an open source policy agent used to enforce fine-grained access control policies. And OPA can be used for multiple environments like Kubernetes, API authorization, CI/CD pipelines, and service mesh, and it's becoming more and more popular every day in the industry. So we use OPA for solving our Linux authorization problems. And once the OPA enforces the authorization, it logs everything into the Splunk. So let's see now, let's get into each of these components and how do they work. First thing that I would like to talk about is the first component is in the client side. So Puppet compiles and it provides a list of information available to each host called host facts. These files include different environment variables and its associated values that can be unique to hosts. For example, these can be like EC2 instance ID, kernel ID, anything unique or like shared among the hosts. In this example, Each host can have like a role that describes what the host is doing, devbox, MySQL, which runtime environment or ecosystem is this host is running, or what is the owner of the host. We can put all this information into the host specs, and it made available to each host. So OPA uses this information, make authorization decisions in the each host. The next component that I like to talk about is that OPA policies and capabilities. So we store authorization policies and authorization capabilities in access restricted Git repository. We created something called authorization capabilities as a set of YAML files, and each capability defines a set of SSH and sudo actions that users can perform, that we specify and put it into the access restricted Git repository. And each capability has a corresponding Active Directory group. So each user can be a member of one or more groups in Active Directory. In this way, we can enforce a strict paper trail policy, and we can distribute these groups based on the needs to each user, like that each user can have the group whatever they need, and we can easily specify in the access restricted Git repository. So like that, we can create least privilege capabilities and enroll the users, these groups. I'm going to go over these capabilities more detail, but first, let's take a look at the OPA policies. So OPA provides a policy specification language called Rego. It's a little bit complex, but after spending a few hours, you can get used to it, which we can write fine-grained access control policies with. And in fact, we wrote two policies for sudo and SSH authorization using Rego. And these policies basically read the host spec data, capabilities map data, and users group, basically all these metadata, and based on the user input sudo or SSH, make an authorization decision. So in this way, the end users never had to look into the complex authorization policies. They only need to modify the metadata like authorization capabilities. Now, let's see an example capability and how we can specify fine-grained access control through the metadata. So here's an example capability. Let's call it OPA Linux Dev Basic that gives a basic access to some dev and test boxes in our environment. So each capability has set of a list of sub-capabilities, and it has to have at least one or more. So it can have one, but it can have more than one sub-capabilities. And each sub-capability matches a set of host specs that we can specify arbitrary host specs in each sub-capabilities. And each sub-capability grant SSH or maybe sudo in the in our ecosystem. Basically, if you look at this example, this first sub-capability allows SSH into unprivileged dev boxes. The second sub-capability allows SSH and sudo in test boxes that are dev or stage ecosystems. So this configuration would allow us to create very fine-grained capabilities and least privilege compliant access control configurations based on our users' needs. The next component that I would like to talk about is that the OPA policy manager. So we wrote some sort of like a microservice that continues to pull all of the authorization policies, authorization capabilities, and Active Directory data, the users group from the Active Directory, and perform some set of like a sanity checks because we don't want to push any bad policies or bad data to client hosts, and combines them into a bundle that OPA can read in the client hosts and push this data to S3 bucket. So up until this point, we've been talking about like all of the metadata that required for making these authorization decisions and made available through the S3 bucket through the clients. Now let's see where actually the authorization enforcement happens in the client hosts. So we run OPA instance or open policy instance running each host. Basically, it reads the host facts and OPA policies, capabilities, and users group membership from the S3 bucket. And it talks with the Linux PAM module or pluggable authentication module and gets the SSH and sudo requests. And based on all these data, make the authorization enforcement and sends the result back to the PAM. And like that, we can enforce the authorization. Once all these authorization happen from each iteration, we log like a well-formatted and standardized logs into the Splunk. The interesting configuration that I'd like to talk about is that our PAM configuration. So that I thought it would be interesting to discuss in this talk. So PAM, or pluggable authentication module, is a mechanism to integrate multiple low-level authentication schemes into high-level APIs. So if we speak basically here, that so PAM provides us a framework to implement different mechanisms to enforce sudo and SSH authorization. So, but PAM is written in C, and it's a little bit complicated, and we could write a PAM plugin in C that talks directly to OPA. And but this would be a special writing C module and distributing to thousands of hosts would be very challenging, especially in a heavy, and it will be dependent on the operating system and C version of the host. And it would be very challenging to maintain in an infrastructure having thousands of machines, especially if we think of like, if you want to support multiple operating systems and multiple versions of these operating systems and C versions, it might not be like forward compatible. So instead of writing our own module, we use the existing PAM exec module that allows us to call any shell script, and we write a simple OPA wrapper script that curves the OPA endpoint and returns true and false. And basically, the PAM module just executes that shell script. In this way, we don't have to deal with any low-level C code, distribution, and maintenance, and we believe that we achieve the forward compatibility. So this was the deep dive into our authorization architecture. Now I would like to show about how does it work in practice with a few different examples. So this is user is happy and try to SSH into a test box, and user has a OPA capability called OPA Linux Dev Basic that give access to test boxes in dev or stage ecosystems. And this user is a member of this AD group OPA Linux Dev Basic, and try to, in first iteration, try to SSH into the test box in the dev ecosystem. So first time when the users try to SSH into the box, OPA is going to retrieve the user's group and then find the corresponding capability. Then it's going to start matching the host facts that is specified in the capability. First, the test box is matching with the role, and the ecosystem is matching one of the ecosystems specified into the capability. And this capability allows SSH. Then this SSH request will be allowed for the user. But let's say the user decides, okay, dev is not enough for me, I want to go to prod. And it's trying to SSH into prod, and the user has only this capability. But this time, since this capability doesn't allow the prod access in the ecosystem, although the role is matching, but none of the ecosystem is matching. So the SSH will be failed to access this prod test box for this user. But what are we going to do if this user is needed and the other users that are enrolled for OPA Linux Dev Basic don't need to access prod access? So what we can do is, in terms of least privilege, we can create a new capability. Let's call this OPA Linux Dev Advanced, and give access to all test boxes in all ecosystems. So it would be like, it will give access to all text boxes on all ecosystems, and we would enroll this user to OPA Linux Dev Advanced. In this way, the user will be able to SSH into the prod test boxes. So this configuration allows us to specify least privilege capabilities and configurations and distribute to the users by their needs. So the next thing that I would like to talk about is that our decision logging. After each authorization enforcement, we collect decision logs in Splunk. For example, for the previous authorization, when the user was denied, we had these example logs. As you can see here, we can see the username, which host name the user tried to SSH, and the SSH result was false. But the interesting thing that I'd like to mention here is that we also log the user's existing groups and the required groups for the user in order for this user to be able to SSH into this box. So this standardized and well-maintained and well-formatted logs actually enable us to make better analysis and getting statistics on the usage patterns in our infrastructure. And like that, we can analyze all of the usage patterns and make least privilege capabilities for our use cases. So up until this point, we deep dive into our authorization architecture, and we have shown that how it works in practice. Now I'm going to hand over to Daniel, that he's going to talk about our rollout strategy in this busy environment and how we ensure the system reliability with the new architecture.
Thank you, Charlie, for the technical deep dive. Rollout strategy. So as with any major system migration, it's super important to consider the rollout strategy. We had a number of goals that were very important for us to ensure the success of this project. It was imperative that we don't block access inappropriately for any human or service users. There were a lot of users in the system and lots of stakeholders that trusted us to deliver this project correctly, and we didn't want to let them down, nor did we want to let ourselves down. Now, for any migration to be successful, in my opinion, you need to really minimize the impact and cognitive overhead for the users of the system. So a primary important goal for us was to make sure that the changes were transparent to all users in the system. And recall, the whole point of this new architecture was to support the least privilege policies as a best practice for all users in the system. However, if we try to change the mechanism for how we do authorization and introduce least privilege permission policies at the same time, it would make it pretty difficult to know if we introduce any regressions into the existing access control semantics. Finally, we knew that our policy wouldn't be perfect on the first try, and we needed to ensure that we could safely iterate on the policy. And of course, communication is important for any rollout strategy. So here are the concrete steps we took to achieve those goals. Every change that we made absolutely had to be rollback safe. In case of any issue, we had to be able to revert the code change and go back quickly to the status quo without any manually futzing about and trying to fix the system. We designed the new system with a dry run mode, which would log the allow or deny decisions it would have made, but not actually enforce these decisions. This allowed us to run the new system in dry run mode in parallel with the old system, and then we could compare the results without impacting access for our users in case of any bugs in our policy or our deployment strategy. So we would roll out our dry run mode incrementally and over-communicate each time we made a change. This was important because even though it was dry run mode, we were still changing core system configuration files, which technically could, and actually did in a few rare cases, cause some kind of issues. Throughout the incremental rollout, we'd monitor our dashboards and logs for any gaps in our authorization metrics, adjust the policies, lather, rinse, repeat, until we got to a 0 diff result. Eventually, we had enough confidence to roll out true enforcement mode incrementally. And here's actual footage of our rollout strategy. There's Charlie and I replacing the wings of the authorization system for thousands of hosts and hundreds of active users with 0 downtime. Our dedication to customer, so what were the results? Our dedication to customer focus, extensive testing, and due diligence ultimately paid dividends as our rollout strategy was wildly successful. We had very few issues that we encountered along the way, and any issues we encountered were trivially able to be rolled back. Since we over-communicated each incremental change, any affected users could easily attribute access issues to our changes, minimizing the mean time to resolution for any issues. Finally, throughout the rollout, we incrementally built a runbook for the new system. Anytime any issue was encountered, we'd capture the characteristics and the behaviors of what happened and how to debug it. By the end of the project, we had a runbook with tons of collateral, and we didn't have to start from scratch at the end of the project trying to scramble and figure out what were all the things that went wrong. We then spent the next whole quarter analyzing the decision logs to understand actual access patterns. A few teams were given a free pass to have administrative privileges due to the scope of their job responsibilities, especially the operations or production engineering team. Every other team was assigned new capabilities based on their actual usage. This was usually really straightforward because we had all the data that we needed. Still, anytime we made a major change, we'd notify teams that their permissions were changing. In most cases, the teams really appreciated the amount of due diligence we put in and had utmost confidence that our changes wouldn't impact them negatively. At the completion of this project, we had no more ops deputies and significantly reduced the number of admins by more than 50%, and each team had their own set of distinct permissions. Now, as you've seen from Charlie's technical deep dive on the new architecture, we actually added quite a bit more complexity under the hood than we had in the status quo. As such, it was extremely important for our design and our rollout strategy to ensure that the system was fault tolerant to any failure scenarios. We maintained a matrix of test cases, and we essentially injected failures in each component and ensured the system reliability. So what kind of things did we test? Well, what if we push a bad policy that has catastrophic side effects like blocking access from all users, or worse, granting access to all users? We do enforce code review, but nobody's perfect after all, and something might slip through. In case this happens, we have automated checks in our CI/CD pipeline that will prevent uploading of a bad policy bundle to S3. Even with these automated tests, it's still possible that a bad policy might slip through. This, or any other kind of issue with the Open Policy Agent service, could cause the service to not respond or respond with a malformed response. To mitigate that risk, we distribute administrators' public SSH keys to all hosts and have a fallback mechanism in our PAM configuration to ensure that even if things go terribly wrong with the authorization system, administrative users can always access all hosts, even if OPA is down. It's also possible that one or more of the data sources used for producing or serving the bundle, the policy bundle, are unavailable. To mitigate this risk, OPA maintains a local policy bundle cache of the last known good configuration. This way we maintain some level of access, albeit potentially a bit stale. This is an acceptable trade-off for our requirements. We have monitoring to let us know when this happens, but historically these outages are quite infrequent and they tend to resolve pretty quickly. Wrapping up, what are the key takeaways that we want you to have from this presentation? While it sounds terrifying and potentially impossible, this project is living proof that it is possible to replace an actively used authorization system with zero downtime. At the time of this presentation, we've been live with the new infrastructure for over a year, and we've never had any access issues caused by failures in the system. This would not have been possible without the upfront planning and due diligence to ensure that we had all the bases covered for migration scenarios and system reliability. In particular, the dry run functionality was really important to know that we didn't have any regressions. The Open Policy Agent lets you decouple authorization policies from any software system. At Yelp, we've now used the Open Policy Agent to provide authorization features across 4 very different infrastructures, including our service mesh, Docker, Kubernetes, and Linux infrastructure. Our experience overall has been very positive. And in each case, we kind of took the same approach of building an abstraction layer in Rego and having the end users only need to make metadata changes to make access control changes. Finally, in the status quo, More than 25% of our users have broad administrative capabilities throughout our infrastructure. This was a huge risk in our threat model. With the least privileged policy infrastructure that we've rolled out, we've significantly improved our security posture and mitigated the risk of internal bad actors or compromised accounts. Additionally, the project has stood the test of time, and we've never found a scenario that we weren't able to provide access for through our infrastructure. Thanks for watching. We'll be available in the chat to answer any questions you might have.